So my name is Vanessa Zawodnik. I'm a junior researcher and a PhD candidate at the Chair of Energy Network Technology at Montanuniversität Leoben in Austria. And I'm going to introduce you to my PhD project, DSM-Opt, which stands for Demand-Side Management, Operation Optimization of Industrial Energy Systems. The project officially started in January last year and has a duration of 3 years. Right now, we are switching from the initial beginning phase, where a lot of coordination, reconciliation work took place, to the operative work. The project is funded by the Österreichische Forschungsförderungsgesellschaft, shortly FFG, and is embedded in the NEFI Innovationsverbund. NEFI, which stands for New Energy for Industry, represents a consortium of experts in the fields of energy research with the aim to launch and support projects to decarbonize the industry. The project consortium consists of 5 project partners. First, we have the IEA INTEC. Some of them are also here today as an independent research facility. Enexa as a software developer, the Chair of Energy Network Technology as a public research institution, and 2 industrial sites. On the one hand, we have the steel and rolling mill Marienhütte in Graz, and on the other hand, we have the bakery Sorger, also in Graz. So, what do we want to do in this project? The major goal of this project is to develop a decision support system toolbox for optimal online process scheduling, including applications for demand-side management functions like energy efficiency, time of use, and market demand response in an interactive and automated way. The 2 work groups that we have in this project center around our 2 industrial sites, meaning that the Chair of Energy Network Technology and Enexa supervise the steel mill Marienhütte, and IEA INTEC deals with the operation optimization of the bakery Sorger. Therefore, as I'm working for the Chair of Energy Network Technology, I will give you a more detailed insight about the steel mill itself and the actual status quo of the project there. The steel and rolling mill Marienhütte is an electro steel plant. Therefore, it uses steel scrap as input for the production process. They produce mostly one steel quality, concrete steel, and form the crude steel to rods and wires with different dimensions in the subsequent rolling mill. And the main energy carriers are electricity and natural gas. And the overall plan for the project started with a process analysis last year. And the aim of this process analysis was to find out which information is relevant for building our models. In autumn last year, the data extraction took place, delivering us a data set with about 280 process parameters. These process parameters were about batch informations like batch numbers, batch weight, produced steel quality, and so on. Process and energy informations about the process temperatures, pressures, electrical power, amount of natural gas, and so on. And information about the production program. After finishing the data preparation, we are right now fully into data analysis, which we will hopefully finish in the next few weeks. And then we will start to build our models. These process models, should be able to live forecast the energy demand for a certain time horizon based on the production program. And these models are the base for the subsequent development of an interactive what-if tool and the optimization. The last part in this project will be the implementation of our findings at the industrial site. So let's have a closer look at the steel and rolling mill Marienhütte, and the data flow and data structure and process structure we have to deal with. Here on this slide, you can see a flow sheet of the process with its main aggregates divided into the steel mill on the left side and the rolling mill on the right side. The steel mill consists of the electric arc furnace, where the steel scrap gets melted. This aggregate is the most energy-intensive aggregate of the whole process chain. So we have to concentrate on this main aggregate for sure. Afterwards, there is the ladle furnace with the ladle heaters, where the melted steel gets a metallurgical treatment, and afterwards comes to the continuous caster. In the continuous caster, the molten steel solidifies, and as an auxiliary aggregate, we have the dedusting for the steel mill. After the continuous caster, the formed billets come to the storage. This storage acts as an N-coupling aggregate in our plant modeling structure. In the following rolling mill, these billets come to the Pascha furnace. In the Pascha furnace, the rods get to the right temperature before they get rolled in the rolling lane. Afterwards, the rods come to the storage, or in case that wires were produced, they can get recoiled in the recoil plan. We are planning to work with two databases to realize this whole project. On the one hand, we will work with a time series database for saving needed information for the live forecast of energy demand, and a relational database management system for saving information that are interdependent and are some kind of information that connects the main aggregates and describe the process logistics, like the batch number. The batch number connects all the main aggregates in a temporal way through the whole process chain, because the batch number starts here and goes through the whole process chain until the final products come to the storage. So much about the theory. The last part in the project is the implementation. And for the implementation at the industrial site, we want to develop a human-machine interface. The plans for setting up this human-machine interface consists of three main parts. The first one will be a live forecast of energy demand based on the production program with a certain time, resolution, and planning horizon. Besides that, there will be a visualization of the interactive what-if tool, showing the changes in the forecasted energy demand if you reschedule charges in the steel mill or change the production order in the rolling mill. And the last part will be a visualization of the forecasted energy demand if you optimize the process schedule regarding to changes in external factors, like, for example, energy prices of electricity or natural gas, or the availability of renewable energy. So I think it was quite short, but I hope I could give you a short insight about DSM Opt, and I will thank you for your attention, and I'm happy to answer your questions if you have any.
Well, thank you for these insights, Vanessa. This does look like a really interesting project. And I'm going to ask the first question right away,
Yes,
which is how does your system interact with the real process, or is it focused on design decisions?
No, there will be a communication between the real system and our models. At the industrial site itself, they have different kinds of data measurement systems, and in the now ongoing data analysis, we are trying to find out the decisive parameters, and when we have them, we will set up a database to extract them in a common way to make them available for our models. But there won't be a connection back to the real system. So it will be just a decision support system, and our models and the forecast and the optimization will not interact with the industrial site and the process itself.
Thank you. And there's another question by Tom.
Yeah, please.
Hello, Vanessa. Thank you for your presentation. You call it a toolbox. Who is going to use your toolbox? Is that more on the energy operator, or is it more the planning of the scheduling if you have made it to an implementation?
Mm-hmm. The plan is that the workers at the steel mill will use this toolbox during the process, during their shifts.
Okay. Because is it possible to make scenarios with your toolbox? So predict more than, let's say, 24 hours ahead?
We are still discussing about the time horizon, which the toolbox should work. Right now, we are at the time horizon for 1 week, so that we forecast the energy demand for 1 week.
Okay, clear. Thank you.
You're welcome.
And maybe on a more technical level, which methods did you use to replicate or to model the process itself and the individual process steps?
We are not at this point for now. That's the next point on our agenda. But we have some findings until now, and these are that because of highly stochastic behavior of the process, we won't be able to do a white box modeling like a physics-based modeling. We will have to use some kind of gray box modeling and black box modeling using machine learning, or some kind of stochastic modeling like Markov chains to represent reality, because especially the processes in the electric arc furnace, as most energy intensive aggregate, is very stochastic and random, and you can't describe it in a physical way.
And what do you expect is going to be the impact of your system on the production process?
The main goal of the steel mill is that they want to reduce their costs per ton of produced steel, and they want to smoothen their energy demand, because they have a lot of peaks and a few high peaks, which drives the electricity price they have to pay, and they want to smoothen that. That's the main goal.
Mm-hmm. Does anybody else